Technology is a wonderful thing. It applies to all facets of life, buildings, transportation, and yes, technology has improved grease ducts too. Actually, one of the oldest grease ducts we've run across was in a 19th century dormitory. The duct was corrugated steel and ran up 3 stories from the basement, using U-shaped metal standoffs to maintain 2 to 3 inch separation from the wood. No fans, just natural draft. The subject of kitchen ventilation was first considered by the National Fire Protection Association in 1946. The first guidelines were included in NFPA 91, known as the standard for the installation of blowers and exhaust systems for dust, stock, and vapor removal or conveying. Following 2 subsequent revisions, it was suggested in 1955 that new guidelines for kitchen ventilation be considered. NFPA 96 made its debut in 1961 and has been the standard for grease duct design and installation ever since. Referenced by all major code bodies and continually updated to address new technologies and safety requirements, the current version is scheduled for revision again in 2011. As technology improved and codes advanced, the standards were raised to welded steel ductwork enclosed in a sheetrock shaft, then a fire-rated sheetrock shaft. Today, mold is a major consideration in this type of construction. Recognizing the shortcomings and inadequacies of those basic systems, NFPA and other code agencies began to look at grease duct more closely, reviewing basic construction, welded joint design, material thicknesses, access for inspection and cleaning, slope requirements, supports, and fire ratings. Next in the evolution of duct design came wrapped systems, the most commonly used system today. The duct is still carbon steel, no changes there. However, listed duct wraps brought 2 significant improvements: reduced clearances to combustibles and higher internal temperatures, thereby reducing grease buildup in the systems and, in many cases, reducing the HVAC load. Installing this type of system requires several trades: the welder to shear, bend, and weld the duct, the insulator to apply the desired insulation, the sheetrocker to enclose and protect the exposed insulation or make it aesthetically pleasing, and several delays waiting for the local code official to approve each step. Today, the largest issue with site-built systems is not the specification, but the end product. This relatively new site-built system got by the local AHJ. It was spec'd as a wrap system. Good thing it wasn't wrapped, or no one would have noticed all the welds were leaking. The discoloration you see is the grease that seeped through the welds. The porosity of carbon steel, in addition to unskilled labor, is the primary culprit. Often additional welding is required to close holes identified with a standard light test. Note in this system the toolless access panel and the liquid-tight construction. Notice the arced weld. The system is flat along the ceiling. Perhaps the arced weld in the bottom of the pipe is the contractor's method of providing slope. Unfortunately, even today, structural designers are not aware of grease duct slope requirements and often fail to provide adequate ceiling height for safe installations. In this picture, you can see a patch scabbed onto a duct section that failed. Judging by the location, the bottom of the duct probably rusted through. This is common with carbon steel duct, especially with water wash hoods and the pooling of cleaning solvents. With a patch welded below the bottom of the duct surface, a low spot was created, simply increasing the problem of pooling. The expansion and contraction of a duct as it goes through normal operational cycles will create torsional forces between the different metal thicknesses and cause premature weld failure. In 2006, a Las Vegas casino experienced multiple leaks in a large section of horizontal carbon steel duct that rusted through. The duct was installed in 2003. The culprit, water wash hoods and water pooling in the bottom of the ductwork. Unless a rectangular flat bottom duct is adequately pitched, pooling is inevitable. In this case, the rusted bottom 1/3 of the duct was cut out and replaced with stainless steel patch of a different thickness. Sometimes duct failures are first spotted when grease runs down the front of the hood. Grease had pooled approximately 3/8 inch deep before overflowing and running down the front of this hood. Had a fire occurred, this reservoir fuel would have really assisted the fire.